Okay, sorry for the interruption. So we were talking about this case here, which is like that. Now, we're trying to find the stiffness of the system relative to this force P. So if this thing here moves in that direction there, then we're going to be ending up with a force here. We're going to be ending up with a resistance here with a stiffness, a resistance due to bending of this member. So this member has an bending stiffness. This member, the bending stiffness is infinite. This member has no bending stiffness, but it's got an axial stiffness of EA, and that is 2. This member is a diagonal member, which can only take axial stiffness, which can only take axial force, and then finally you've got this member there. So we could say that our P is being supported by 4 springs. So one. So that's another spring, and then that's another spring. So I've run out of space, as you can see. It's got 3 springs. Let's say that this member here doesn't have any stiffness. So I'll call this one member number 4. I'll call this member number 1. I'll call this member number 2, and I'll call this member number 3. Okay. So if this moves across, so I'll draw it on top. So I'm going to be messing up the drawing, of course. So I'll draw out the movement. So if it all moves across by a distance delta, you can see that this member here, member number 2, is going to extend or get longer. You can see member number 3 has deformed like so, with that being 90 degrees and that being 90 degrees. Hence this bending stiffness here. And you can see that this member has also moved across like that. So we're interested in the stiffness, or calculating K of the entire system, and by observation you can probably see that since there's going to be no bending moment, there's going to be no stiffness on this system with respect to member number 4. So we just need to work out the stiffnesses of this bit here. So that would be the K due to 1, or the stiffness due to 1. The stiffness due to the extension of that member there, and then the stiffness of the bending stiffness of that one. So there's going to be 3 stiffnesses that I'm going to have to calculate. So we'll show how to do that later on. So let's have a look at how we might want to represent this. We could say we apply P. So we're applying P, and it's going to be equal to a stiffness, which is going to be called K. So this is the stiffness of the whole system, which is just going to be K1, K2 plus K3, multiplied by the movement that this bit has gone through. So let's talk about the bending stiffness first, because this one's probably the most difficult one to do, and it's just one piece of new information compared to what we've done before. So you can see that this is being displaced by a distance delta. So this was originally like that, and it's now, so both ends are fixed in. Both ends are fixed, so the bottom is fixed and the top is fixed because it's moved to a rigid case, and it's being forced to move a displacement delta, and then the delta bit is going to lead to something like that. Okay, so after it's been displaced by delta, it's going to have moved like that. Let me get rid of the original one here. So we can probably feel that there's going to be a moment there at the end, and we could probably feel that there's going to be a moment there at the end. So we can probably feel that there's going to be another moment at the end here, and that one would have to be going in that direction. If you're having trouble figuring out which direction, maybe if you just imagine something like that, you could probably see that that's going to have to push it back so that that goes there, and then that one goes in the opposite direction, which would be to push this more so that it comes out at 90 degrees. Okay, so that's how to get the direction of the moments at the end. And I was looking for the fixed end moment drawings, but of course there's no fixed end moment in this case because it's just a displacement that has been applied at the ends. Let's have a look at, let's go back to here, and we can see this formula here, MAB, and then I cancelled out this relative bit here because I said it's not needed for the no sway frames, but this one here that we're looking at has got some sway, of course. So when we look at this, this bit here, delta A minus delta B, is the displacement of end A relative to B, and of course that's going to become our delta. All right, and there's going to be no fixed end moments when I write out that equation, okay, because MFAB is going to be 0. So and there's going to be no fixed end moments because I've not applied this, there's no force, no lateral force or moment applied between A and B. All that's happened is that we're pushing the frame to one side. Effectively the frame is going under sway. So we've got AB. So here's the equation: MAB minus MFAB. So we're just dealing from the A to B's, is equal to 2EI. Now let's get some geometry of the frame, which we see here. So the frame is of height H, and it's probably of length L. So it's of height H and length L. So this height is here. Okay. So 2EI over the length, 2EI over L, which would be the H in this case here, and is going to be 2 theta A plus theta B, which is of course 0, and then it's going to be minus the 3 delta differences between those A and B, which is going to be delta in this case here, and then according to the equation it's going to be divided by H. So the only new bit that we need to worry about in this case here, the only new bit that we're going to have to worry about is this bit here, the 3 and the H. Okay. So now we know that the fixed end is going to be 0. We know that this theta A is going to be 0, and we know the theta B is going to be 0. So MAB has worked out to be negative 2 times 3 is 6 EI delta over H squared. So we've got this delta. I really apologize for the kids bothering me. 6 EI delta over H squared as the equation for here. So we can see that if we adopted the idea of clockwise being positive, so we'll put a clockwise moment, which would be here, and then we also put a clockwise moment here. That would be minus 6 EI delta over H squared, and we can see we need to get rid of the negative sign, and that would change the angle, change the direction of the arrow, which of course is what we have here. So we've been able to get the moment at the end, EI delta over H squared. I'm recording, Emily. I'm recording. Okay, alright. Thank you. So, we've now got the 6 EI delta over H. And what we really want to do is we're pulling the frame across so that it deforms in this shape here. And there's going to be a force at the column base. So to get the force at the column base, if you wanted to, you could of course draw the bending moment diagram. So this would be on that side there, and then that side there. And then to get the shear force, if you really wanted to get the shear force diagram, the shear force diagram would look something like that. And then of course that force there is going to be the base shear that we're after, which is going to be just the gradient of that line. So the gradient of that line is 6 EI over, 6 EI over H squared, 6 EI over H squared, so that's 12. And then that's all going to be divided by H, because the shear force is the gradient of the bending moment diagram, and that will give rise to that. So this would work out in that direction to be 12 EI delta over H cubed. So I said there were 3 springs. So when Na'awi in the 3rd year asks you what the stiffness of this is, what he really means is the sum of each. What he really means is work out the stiffness of each spring. The 4th spring, of course, not taking any load. So the stiffness of this one here, which would be the 3rd one, that's going to be here. So 1, 2, and 3. The 3rd one is going to be 12 EI. So that's going to be 12 EI delta over H cubed. Okay, and I think I'll get the delta outside, because we know that the stiffness is P times the stiffness. P is equal to big K, i.e. K1 plus K2 plus K3 multiplied by delta. Okay, so I think I said before this could be solved using the flexibility method, but you can see that it's a bit simpler to solve using the stiffness method in terms of getting the stiffness of this. So there's going to be 3 components. The first component, of course, is going to be the extension of this bar here. So the extension of that bar is going to lead to a stiffness P. The extension of here, So we would be writing delta, just concerning with this bar here being extended, is equal to P times the length of the bar divided by EA. And we've already said that the length of this bar here is L2, so the force times L2 divided by EA is going to be equal to the delta, or the other way around, P is equal to delta times EA over L2. So the stiffness here of the bar, when we put into this format here, which we can just drop in, is going to be nothing more than EA over L2. Okay, so hopefully you can see how that's been rearranged for the stiffness. EA over L2 times delta, EA times delta over L2 is going to be equal to P, or the component of P representing that one, which is going to be EA over L2. Okay. Okay. So then we've got one more, which is going to be the stiffness of this bar that we've drawn there. So if we said that the bar was going to be extending by a distance delta, we can draw this here. Okay, so that's the original place, and then it's been displaced as it's a pin by a distance delta. Okay, so it's been displaced by a distance delta up there. So just imagine that point moving to that place by this distance delta. So there's going to be an extension to this bar here, which I'm going to be calling delta. Okay, and then I'm going to be writing delta is equal to original length. Well, I'm going to be using similar triangles, and I'm going to be able to get an expression just from the similar triangles in terms of both sides. That is delta equals L divided by A. Delta is equal to L divided by A multiplied by that distance there. Okay, so that's going to be the extension of this bar here, and the original length of that bar here I'm going to be calling A. Okay, and A is square root of A is clearly equal to the square root of h squared plus L squared. Okay. So we've got that expression there. So now the force in the bar is going to be, so we're going to say the force in the bar from similar triangles is going to be, changing is equal to that, which is equal to L over A. And then I'm now going to be substituting it in, and from there I'm going to get EA for the stiffness, delta divide by A. And from there I'm going to be getting EA L over A squared delta. So we've got a force acting in the bar, and then I need to take the component of that force in this direction here. Okay, so that's also the base shear, so we've extended it in one direction there. And yeah, if you did that by going that force there in the bar and then take the sine and cosine of that one, you're going to be ending up with this force cosine that angle. And if you did that using the cosine is that over that, you're going to end up with EA delta over A L squared, and it's going to be A3. Okay, so EA delta L squared over A3, which means that I can now slot that, so that is the force, which is obviously proportional to the delta, and then I can slot that into EA over A cubed L squared. Okay, so in terms of this stiffness here, so we say we're going to pretend all that is a blob with one stiffness under a force P. So when we say what's the stiffness of this, we applied a force there, we would be saying that that can be represented by one single spring, which is the addition of K1, K2, K3 and K4, remembering that K4 is 0, and that stiffness of the spring is equal to EA over L2 plus EA L squared over A cubed plus 12 EI over H cubed. Okay, and then this is what's known as the stiffness of this system here. So to get that, the only new bit sort of is the use of that bit of the slope deflection with the 3 that I deleted right at the start because we weren't covering no sway frames. But I'm showing we weren't covering sway frames, but now I'm showing how that sway component can be used and then added to the other 2 bits that you already know to give you the stiffness of that. Okay, so at this stage, if you go into the Dropbox, remember any question on this stiffness stuff is completely optional. You can always do question 3, you don't need to do question 4. But if you wanted to look here, there are 5 questions. There are 5 questions that notes have been provided for. So, sorry, 4 questions. So one, we've had a look at these 2 plus this one here, and then this one here is very similar to this, except the heights are different and that there is a rotational spring there, but that's the only difference. And the one that we've just been through, Puya has done a video where he gives more detail than I have. So he's prepared a written solution for it, and he's also provided a video that goes through how each of the bits work out. Okay, so yeah, so there's a video where he explains what I've just covered a bit slower, and then he's also got videos for that one, and that one, which you can have a look at. So that one would go onto there, and then he's also provided other solutions. Okay. There's also a set of notes about stiffness if you wanted to have a listen to them. So he's provided a set of 4 lectures giving a bit more background to what is actually meant by stiffness, and hopefully that would help you to transition into year 3 when Ali will be talking about stiffness straight away. So he would be using terms like what is the stiffness of this, and he would expect you to be able to write that out he would be expecting you to be able to write out what we've just written there. Okay. So sorry for the interruptions. I'm just one. So sorry for the interruptions. And if you've got any questions, just talk to me on Piazza, or get in touch with me by email, and we'll try and answer your questions.